terms added to a smooth objective. Okay, I'll talk about accelerated gradient, which people in machine learning got very excited about starting, 10 or 12 years ago. I'll talk about stochastic gradient. This really is the workhorse algorithm for training neural nets. And we came across it last night. I actually told you what it was last night, but I'll remind you again. There are so-called variance-reduced hybrids. There are these modifications of stochastic gradient. I'm not sure if they're used that much in practice, but you can think of them as being hybrids between the full gradient method, which is the standard first order method here, and the stochastic gradient method. So we'll see that. I'll say a little bit about coordinate descent. A very recent topic is primal dual methods for min-max problems. I told you last night what min-max problems were, and I'll tell you again tonight. And I guess it's midday your time, it's tonight my time. And then if there's time at the end, I'll talk about augmented Lagrangian and ADMM, which also have been quite popular. So here are three kind of classical structures that arise in data science applications. The first one we've already come across a lot in the first two lectures, and that is this finite sum form. And so the objective that we're trying to minimize is the sum of a bunch of other objectives. They all depend on the same variable x, which can be a very high dimensional variable. And we just aim to minimize the average of those m terms. And m can be very large as well. And I've explained the reason for that kind of structure. And it turns out a lot of the algorithms we talk about exploit that kind of structure. Now, in some applications of machine learning, these FJs are convex, like in kernel learning and logistic regression. But as I've said recently in neural network training and low rank matrix problems, there's been a lot more interest in non-convex problems. Suddenly people started to get interested in that about, 7 years ago or so. And now they've really taken over non-convexity. So that's the first kind of structure. The second one is where you take an objective, and it often is this kind of finite sum objective, but you add on what's called a regularization term times some parameter, some positive scalar lambda. Now this function psi is typically non-smooth, and often it's also non-convex. So the classic version of psi is just the L1 norm, which is non-smooth and convex actually. And adding on some multiple of the L1 norm to your objective tends to give you a solution where x has a lot of zeros in it. So x has n components, but most of them will be zeros if you add on a term like this. And the bigger you make lambda, the more zeros there'll be. So adding on this kind of a term is a way to explicitly introduce structure into the solution. So by doing that, if you choose the psi, the function psi, to induce the kind of structure that you're looking for, so when you use the one norm, you're looking for sparsity. That is, you're looking for an x that only has a few non-zeros. But there are other kinds of structure as well. There's a thing called the total variation norm, which is used in image processing, which introduces a kind of structure in the solution that tends to promote images that really look like images with large areas of constant color and sharp boundaries between them and so on. So you have to choose the psi very carefully to match the kind of structure that you're looking for. And then you have to figure out how to choose the lambda to sort of decide a trade-off between sort of fitting the data, which is the F term, and getting the kind of structure that you want, which is the psi term. So anyway, this is another very common form of problem that we're called on to solve in machine learning. And the third one is just an objective, minimizing the objective subject to being inside some closed convex set. And sometimes this is kind of an alternative to the second problem. So you sort of have the choice between minimizing f of x plus lambda times the one norm of x, or minimizing f of x subject to the one norm of x being less than or equal to some value r, say. Okay, and these two things are actually the same for appropriate choices of lambda and r. Now this constraint doesn't quite have this form, but you can write it in this form. You can say that, basically you can say that x belongs to kind of a diamond shaped set. which sort of captures this behavior. So in other words, this last form of the problem is kind of an alternative to the second form, the regularization form, that's often useful in practice. Okay, so another comment is that when machine learning started to come to optimization and to draw on methods from, heavily on methods from optimization, starting really in the late 90s, I suppose, they often sort of looked for methods that were in some cases out of favor, or methods that had been around in the optimization literature for a long time, but people weren't really paying that much attention to them anymore. So one, maybe the most famous example, second most famous example of this is Nesterov acceleration, which had been around in some form since the 70s with Polyak's heavy ball method, but Nesterov came up with a particularly neat version in the early 80s. And this is one of those Russian papers. It's only 2 or 3 pages long, but it has had enormous impact. So that people in optimization, some people knew about that. I didn't really know about that, but the machine learning people really latched onto it, starting in about 2010 or so. Now, I said that was the second most famous example. The most famous example, of course, is stochastic gradient, which was proposed by Robinson Monroe in 1951, and it just kind of sat there for decades, and people didn't really use it until the machine learning people discovered that it was exactly what you needed to solve problems like this here. And so, of course, that's become the absolute workhorse of machine learning. But there are other examples as well. ADMM, I kind of do remember the birth of that because I was talking to John Eckstein a lot at the time in the early 90s when he was writing his thesis. So I knew about ADMM, but again, that's one of those things that sat there for, for 15 years or so. This famous review paper was written in, I guess, in 2011 by Eckstein and Boyd and several others that now has a gazillion citations where they sort of popularized the use of ADMM in machine learning. Other things, parallel coordinate descent and parallel stochastic gradient. These are things that I worked on a lot about 10 years ago, but a lot of the early work in that was done by Dimitri Bertsakis and John Tsitsiklis at MIT, and they have this wonderful book from the late 80s, which again, I got a copy of at the time it came out when I was at Argonne, and we used to refer to it there. But this work, again, is one of these things that just kind of sat there. It came out of the fact that in the 80s, people got very interested in programming on parallel computers. But it wasn't until machine learning came along where people really had applications that cried out for the use of parallelism. So this work became a big deal at that point. And then this other famous example of the Frank-Wolf algorithm. I heard about this when I was at North Carolina State in the 80s, but it was invented in 1956. And if I do get time in this talk, I'll mention it at the end. It's an algorithm for solving this problem, where you're minimizing, in fact, a convex function over a convex set. But it's one of these things that just sat there for a long time, and occasionally people would work on it, but it didn't really get a lot of attention until there was a paper by Martin Yagi in 2013, which got a lot of attention and really popularized the use of Frank-Wolf or conditional gradient methods. Okay, so the story here is that, the optimization toolbox had a lot of algorithms in there, and some of them were, not very high profile in the optimization community, but some of them turned out to be exactly what the machine learning people needed. All right, so a few preliminaries here. When I talk about convex functions, I talk about this definition. So for all x and y, I'm missing part of the definition here. For all x and y, and for all alpha between 0 and 1, if this inequality holds, then you've got a convex function. And it's much easier to see if I draw a picture. A convex function looks like this. Okay, so if x is here and y is here, and then if I draw that, the right-hand side of this expression is just a line that joins xf of x to yf of y. And if that line lies above the actual function, on or above the actual function, then I've got a convex function. So that's what it looks like. There's a property here that when f is convex and smooth, we've got this property that the tangent at x to the function or to the graph of the function lower bounds the actual function. So the picture of that is easy to draw. If this is x here, the right-hand side is just the tangent that matches the slope and the value of the true function at the point x. And as you can see, the tangent lies below the actual function value at all points y. If I pick any other point y, we'll have that property. So strongly convex is one where it's like convex, but there's kind of an extra quadratic term added here. And in fact, this function that I drew up here is an example of strongly convex, where the left-hand side is kind of strictly below that interpolating line, okay? And if it's strongly convex and smooth, we have not only is it greater than this tangent, but it's greater than this sort of convex quadratic. It's lower bounded by a convex quadratic. So I can draw a picture of that too. So this is the true function. No, that's not, yeah, okay, it's got to be a function, so it's got to be like that. So if I've got another, if I pick a point x here, and if I form this quadratic for some gamma greater than 0, I get another function that's almost the tangent, but it has a little bit of positive curvature to it as well. And it lower bounds the true function. So if I can do that for some, at all points x for some gamma, then I'm dealing with a strongly convex function. Okay. All right, so a few more preliminaries here. You're an optimization audience, so you know this stuff cold. But if you're trying to minimize, do an unconstrained minimization of a function f, the first order optimal conditions are simply that the gradient is 0. So if f is smooth, then any minimizer of f has got to satisfy this property. If f is also convex as well as being smooth, this property is sufficient as well as necessary. So it suffices in the case of a smooth convex f to just look for a point that satisfies this property here. Now, again, if you're dealing with a smooth f, a second order necessary condition for optimality is the following. So not only should the gradient be 0, but the Hessian of f should be positive semi-definite. And again, if x star really is a minimizer or local minimizer of f, and f is smooth, it's got to satisfy these conditions. Okay, and then finally, I'll just say something about non-smooth functions. So if psi here is a convex function, but not necessarily smooth, I've chosen the notation there deliberately because this function psi here in this regularized form is often like this. It's convex but not smooth. Then we can define this thing called a subgradient. And the subgradient basically is the slope of any supporting hyperplane to the function psi at the point x. So I can draw a function of this as well. So here is a function that is convex and non-smooth. And if I just focus on the point here where there's a kink in the function, then obviously I can draw a bunch of supporting hyperplanes that go through the graph of the function at that point. So here is one. Actually, I'll just draw it as a solid line. So that's one supporting hyperplane. Here is another one. Here's another one. Okay. And each of these corresponds to a different value of g. And each of those g's is what we call a subgradient. Okay. And the subdifferential is just a collection of all the subgradients at a given point. So if the function is actually smooth, there's only a single subgradient, and that, of course, is just the gradient. Okay. So the definitions of subgradient and gradient coincide for smooth functions, smooth convex functions. Okay, and the last one, which turns out to be quite important, when we're talking about smooth functions, often what we mean is that the gradient of f has this Lipschitz continuity property. That is, if I evaluate the gradient at 2 points, x and z, then the difference of the gradient, the norm of the difference, is bounded by some constant L times the norm of x minus z, okay? And this L turns out to play a very important role in the analysis and in the definition of some critical algorithms. So one very simple consequence, which comes up a lot in the algorithm design and analysis, is the fact that if we've got a smooth function that satisfies this property, doesn't have to be convex, just smooth, then you can upper bound the function at a point z by this quadratic in z, okay? You can see this is quadratic, and this is for any x and z, okay? So in other words, I can sort of at the point x, I can form this quadratic using the function value at x and its gradient, and I can add the quadratic term as a very simple term. It's just the norm of z minus x squared times this L, this Lipschitz constant L. And that turns out to be an upper bound on the actual function. So a picture of that might be something like this, okay? And here is my point x, and the right-hand side, let me draw the right-hand side. That's going to be a quadratic. It's going to look something like this. It's going to match up with the true function at that point, and it's got to be a quadratic, so it's got to be, you know, shaped like that, okay? So that's the picture of, so the right-hand side is this object here. Okay, very good. So, so much for the, well, I'm not quite done with the preliminaries. There's another one that's quite interesting here, and this is something that we need, particularly when we're dealing with convex, but not necessarily smooth functions. There's this thing called the MoCaO envelope, and you can think of it as kind of being a smooth version of H, where H is our convex, possibly non-smooth function. And it's defined in a way that I can't really motivate too much in a short time, but basically you're given an H, you're given a scalar lambda, and you get the value of the MoCaO envelope at a point x by plugging x into this formula and taking the infimum over u, okay? And I can pull out the 1 over lambda and define it like that. Now, when I write it in this form, the reason I wrote it in this form is that we've got a name for the u that achieves this infimum here. We call it the prox operator. It's the prox operator on the function lambda h. And that turns out to be very important in algorithms, as we'll see in a moment. So this MoCaO envelope, it's a very useful concept. First of all, even when h is infinite valued, even when h has a domain that's you know, not the whole space Rn, but it actually goes infinite at some points. Even when that's the case, the MoCaO envelope is always finite at all x. Okay, so it's got sort of nicer properties. And not only that, but it's differentiable. You can actually show that the gradient of this MoCaO envelope at the point x is given by this formula. I just calculate the prox and plug it into this formula. So it's convex, smooth, it's always defined, and it's differentiable, in contrast to the original H. So it's a very useful proxy for H in several contexts. And the other thing here is that X star minimizes H if and only if it minimizes the MoCaO envelope as well, okay? So it really is useful in that sense. All right, so finally, let's talk about some algorithms. So here's the simplest one, steepest descent. And this is the foundation of an awful lot of algorithms in data science. In fact, most of what I'm talking about today is founded in this very simple algorithm. And the idea is we're trying to minimize, unconstrained minimize f. And the idea is we calculate a gradient and simply take a step in the negative gradient direction with some step length alpha k. So totally intuitive thing to do. You just move in the direction where the function is decreasing the fastest. Okay, and this is very easy to analyze. In the case where you've got an f that has this Lipschitz gradient property that I talked about earlier on, where the gradients were Lipschitz continuous with Lipschitz constant L. So in fact, if we just make the choice of alpha as 1 over L, for all k, we always use the same step length, we can actually show that that choice of step length produces a guaranteed improvement in the function at every iteration. And I can prove that by just going back a couple of slides and looking at this formula, which this formula here, which I've scribbled all over. So let me erase all the scribble. Okay, so this formula here, what I'm going to do is I'm going to plug in x equals xk, and I'm going to define z to be xk minus 1 over L times grad f at xk. Okay, so I make those substitutions, then z minus x is just minus 1 over L times grad f of xk. okay? And then this term here is going to be the norm of that thing. So if I make all those substitutions, you can see I've done that there and there, I end up with the property that f of xk plus 1 is bounded above by f of xk minus this positive quantity here, 1 over 2L times the gradient of f squared. Okay, so we get a guaranteed improvement. Whenever we're at a point where the gradient is non-zero, this is guaranteed to give us a better value of f. Now we can use that to prove various complexity properties about how fast this method converges. So, and these are the ones that I'm going to prove at least a couple of, just to show you that there's nothing scary about these proofs. You really can prove them in a slide and a half. So here's the first result. It says if you run that method using that step size, the 1 over L step size, and you run it, say, for big T iterations, then what this result tells you is that if you look at the minimum gradient norm that you encountered in the first T iterations, that's bounded above by this quantity that is order of 1 over square root of T, of big T. So basically this tells us that the best gradient that you encounter in the first T iterations goes down like order of 1 over square root of T. So obviously as big T goes to infinity, this gradient, the best gradient you find is going to go to 0, but it not only tells you that, it tells you how fast it's going to go to 0, okay, which is useful to know in a lot of, when you're doing theory. So I've got a proof of this. In fact, it only takes half a slide. The whole proof is here. And the proof is based on taking this inequality, which again, I've scribbled all over, so I'll erase that. But it's just taking this inequality here and rearranging it. It's putting the gradient of f squared term on the left-hand side. It's taking the f of xk plus 1 term over to the right-hand side, and it's multiplying both sides by 2L, okay? So I'm getting gradient of f of xk squared less than or equal to 2L times the difference in functions here. And then I'm just summing over both for k going from 1 up to t minus 1, summing both sides. Okay, so what happens on the right-hand side is this very familiar and useful thing called the telescoping sum. And what that means is that the xk plus 1 term cancels with the f of xk from the next term in the sequence. So when you write all these out, you get a ton of cancellation. And all that's left after you sum from 0 up to t minus 1, all that's left is the very first term, the f of x0 from the first term, and the f of xt from the very last term. Everything else just cancels out. Okay, so I've got that the sum of all the gradients squared is bounded by this constant. Okay, and I'm assuming here that f is bounded below by f bar, right? So I can say that this is less than or equal to f of x naught minus f bar, because f of xt has to be greater than f bar, all right? And then at that point, all I do is just take the square root of both sides and use the fact that the minimum is less than the average, okay? So if I take the minimum of all of these squared gradients that I encounter so far, the minimum is less than the average of all the squared gradients that I've encountered so far. So I just take the square of both sides, including this side, and I get the result. And you'll see the 1 over t here appears under the square root, okay? So we've got that even for a non-convex function, as long as it has this Lipschitz smooth gradient property, we can show that the gradients go down like 1 over square root of t. Now, if in addition we've got that f is convex, we can say more. We can say that we actually get a faster convergence rate, 1 over t. Now, we're using a different measure here. We're no longer using the gradient of f or gradient of f squared. We're actually using the difference in function value between f of xt and its optimal value f star. Okay, and we're actually just going to use the same inequality from here that we proved a couple of slides ago, but we're going to use the fact that because f is convex, one of the properties of convexity that I showed you earlier was that the function is bounded below by its tangent at any given point. So I just apply that here, and I'm able to substitute for f of xk in the right-hand side of that expression, unable to bound f of xk above by f of x star minus that term. Okay, and now I just do some clever rearrangement. I take these last two terms and express them as a difference of these two quantities here. And then I notice that xk minus 1 over L times grad f of xk, that's just xk minus 1, okay? So we end up with how f of xk is equal to the optimal f plus L over 2 times this difference. So you can all guess what I'm going to do now. I'm going to use our old friend, the telescoping sum idea. So I'm going to sum both sides up from k equals 0 up to t minus 1. And once again, I get this cancellation in the summation on the right-hand side. And all that's left is the first term and the last term. And this last term has got a minus in front of it, so it's a negative. I can just drop it and just write it as less than or equal to the first term. Okay? Now, once again, here I'm able to use the fact that the difference between f of xt and f star, because f is always going down, the difference between f of xt and f of x star is less than or equal to the average of the differences between f of xk and f of x star. Okay, so the minimum is less than the average. And we've just shown, if we divide both sides of this expression by t, we've shown that this average is less than L over 2t times the distance to the solution. So we're able to show that the non-optimality in f goes down like 1 over t. Now, when you're dealing with a strongly convex f, this is now a function f that's bounded above and below by convex quadratics. The lower bound has curvature gamma, the upper bound has curvature L. You're actually able to prove something even stronger. You're able to show that the difference between f of x k plus 1 and f of x star is less than or equal to some fraction less than 1 times the difference between f of xk and f of x star. So you're actually making a substantial improvement of at least a certain factor, strictly less than 1 at every iteration. And again, you can do that. Again, you work with this, the fact that you've got this quadratic lower bound on f of y. So you write that quadratic lower bound that I wrote a few slides ago. You minimize both sides with respect to y. On the left-hand side, when you minimize f of y with respect to y, of course, you just get f of x star, where x star is the solution. On the right-hand side, it's a simple quadratic. So when you minimize that with respect to y, you get something else. And when you plug in that solution, you get this, okay? So by manipulating that, I'm able to show that the gradient of f at x squared is bounded below by 2 times gamma times the suboptimality in f. And now all I do is just go back to our old friend, this expression that we've now used twice before. This is the third time. And I use this lower bound that I just proved to get an upper bound on minus the gradient squared, okay? And I end up with this expression here. And now all I do is just substitute f of x star from both sides, and I end up proving this thing that I tried to prove. Okay, so this is much faster convergence. This is much faster than 1 over square root of t or 1 over t. This is actually geometric convergence. So this will show us that f of xt minus f of x star is less than or equal to some rho to the t times f of x0 minus f of x star. Right, so it's much faster convergence, provided rho isn't too close to 1. Now, you can turn these convergence rates into so-called complexity expressions. So now that we know how rapidly these functions are converging to their optimum, we can ask the question, how many iterations t do we need to reduce the suboptimality below some threshold epsilon, okay? And so we can easily convert each of these rates into an expression telling us how big t needs to be to reduce the tolerance, to reduce the suboptimality or whatever we're working with below epsilon. So it's sort of easy to see that if you've got 1 over square root of t, something that's over 1 over square root of t, and you want to get that to be less than epsilon, this is telling you that t is going to have to be greater than or equal to order of 1 over epsilon squared, okay? And similarly, if you're dealing with something that's going down like 1 over t, you're going to need t greater than or equal to order of 1 over epsilon. The interesting one is this last one. If you've got this geometric rate of convergence, where the constant in the geometric rate is 1 minus delta for some small delta, you can show by taking log of both sides. You start with 1 minus delta to the t, less than or equal to epsilon. You take log of both sides and solve for t, and you end up with log epsilon over log 1 minus delta. And because log 1 minus delta is close to minus delta, this is approximately log epsilon over delta. So, you know, provided delta isn't too small, log epsilon, if epsilon is something like 10 to the minus 6, log epsilon is kind of only order 6, whereas 1 over epsilon squared is 10 to the 12, and 1 over epsilon is 10 to the 6. So obviously having something that's logarithmic is generally much, much better. And so there's a big advantage to having a strong convexity here. Okay, so that's just unconstrained smooth function. What happens when we add on this regularization term? Well, basically we do the same thing, but we account for this regularization term explicitly. So this is a so-called Prox gradient method. It's the sort of most natural extension of the negative of the steepest descent idea to the case where you've got a regularization term added on. And the idea is we just, first of all, we ignore the psi and we just take a negative gradient step in F, but then we account explicitly for psi by using this prox operator. So you can think of this as the following. You can think of this as writing an approximation to this function based on xk. So let's take the gradient at xk, let's take the point xk, and let's approximate f of xk by, let's approximate f of x by these terms, the gradient, which is obviously, you know, a first order approximation, plus this kind of second order term, which is a very simple second order term because it's got the Hessian as a multiple of the identity. And let's leave the last term alone. Let's not approximate the psi term. Let's just deal with it explicitly, okay? So it turns out that this is how you get the next iterate, and that's equivalent to applying that prox operator that I defined a few slides ago, okay? So not surprisingly, this algorithm has many of the same properties as steepest descent for the smooth case. So for example, if you've got a convex, if both f and psi are convex, you're able to show that you get a 1 over t type convergence rate. I've changed the notation here to k instead of t, but it's the same kind of convergence you got in the smooth case. And you can show that the other types of convergence generalize as well. So we can sort of deal with the regularization term pretty easily. Now, an interesting thing to note here is that this is we can use that regularization formulation to write the constraint problem. So if I'm minimizing f over the set omega, I can rewrite that as an unconstrained problem where I'm adding on a regularization term, which is an indicator for the set omega. So this indicator function has value 0 when you're inside the set and infinity otherwise. And I can treat that as a regularized optimization problem. If you do that and apply this Prox gradient method to this formulation, you actually end up with something called the gradient projection algorithm. And the gradient projection algorithm just says, take a negative gradient step in F and project back onto the set omega. So I can draw a picture of that here. So if this is your point xk, I can take a step in the negative gradient direction, and I can get my next iterate by just projecting that back onto the set omega, okay? And that's a, you know, well-known method. So Prox gradient is related to sort of familiar methods. Okay, so I've got to speed up a little bit here. So accelerated gradient, this was this method of Nesterov. It had actually been around in various forms before that, but it's a very cool idea because it still only uses gradient information. So it takes a step that looks a lot like steepest descent, but then it also adds on a multiple of the step that you just took. So it takes a difference of the last two iterates, which is the step that you just took, and it adds on a multiple of that to get you from xk to xk plus 1. And that turns out to be a powerful idea. It's not obvious at first glance why it should be, but you remember that this iterate in turn was based on the gradient at xk minus 1 plus some multiple of the previous step. So this basically encodes all the gradients you've seen so far. This encodes the gradient of f of x naught, the gradient of f of x1, and so on. up to the gradient of f at x k minus 1. So in other words, it's kind of a very compact way of using not only the latest gradient information, but also all of the gradients you've seen up till now, okay? Now, Nestrov's method this is the so-called heavy ball method. And this is described, I think this dates to the 70s, Polyak and possibly others. Nestrov's method is very similar. The only difference is that it takes this so-called momentum step before it evaluates the gradient, okay? So it doesn't evaluate the gradient and then take the steepest descent and momentum step. It takes a momentum step first and evaluates the gradient at that point rather than at xk. That's the only difference, okay? Well, the other difference is that it uses different formulas to decide on how to choose the alpha and the beta. So here are some results. I'm not going to try to prove these. It turns out proofs of Nestrov's acceleration results are much more complicated than the simple proofs I just showed you for steepest descent. If you make these particular choices of alpha and beta, we just choose alpha to be 1 over L, just like we did in the simple algorithms that I showed you earlier. The beta ends up being something pretty close to 1. It's defined in terms of this other sequence lambda in a complicated way. But I'll just cut to the chase. What you can show is that when you apply this to a convex function, you get over 1 over t squared rate. And that's better than the 1 over t rate that we got for steepest descent. Okay, so this means that if I'm trying to converge to a precision of epsilon, I'm going to only need order of square root of epsilon iterations to do it. So if epsilon is 10 to the, square root of 1 over epsilon. So if epsilon is 10 to the minus 6, then I'm going to need order of 10 cubed operations, whereas in steepest descent, I'd need order 10 to the 6 iterations. And notice I'm only evaluating the gradient once at every step, so I'm not really missing out on anything. There's a version of Nestrov acceleration that works for the strongly convex case. If I know this so-called modulus of convexity, the curvature of the lower bounding function, I can choose the beta in a different way, and I can get a faster convergence rate. You remember the convergence rate in this case for steepest descent was 1 minus gamma over L. Now it's 1 minus the square root of gamma over L, which is a number that's further away from 1. So it's faster convergence, okay? Okay, so now you want to ask the question, I've told you about methods that use the full gradient, but do they actually make sense? And that's a reasonable question to ask because when I'm dealing with this finite sum form of the function, in order to evaluate the gradient of f, I'm going to have to evaluate the gradient of every single term in the sum. And if m is in the billions, this is a tremendous amount of work, and I just can't afford to do it. And so we look for alternatives to this, and the alternative is the one that's most often used is the one I showed you last night, which is stochastic gradient. And in stochastic gradient, you just pick one term in this sum at random. We just pick at iteration k, we just pick a jk. We evaluate just that gradient in the sum. We don't evaluate all m of them, we just evaluate a single gradient. And that gives it, and then we take a step in that direction, okay? That's all stochastic gradient is. Now it's unbiased because I made a random choice of term in the sum. It's easy to see that the expectation of the gradient that I've selected actually is equal to the average, okay? So it's an unbiased estimate of the gradient, but its variance might be very large. The individual terms in this sum of gradients might be very different from each other. And so there is a little bit of information in this step, but there's also a lot of noise. And so it's going to need many, many more iterations to converge than just the straight gradient method. So sometimes we don't just look at the convergence of xk, we actually take an average or some sort of weighted average of all the iterates we've seen so far. And we sort of prove things about the convergence of that object. I've got a few results here for convergence of stochastic gradient. I don't really have time to go into them in any great detail, but they sort of all depend on how wildly are these individual gradients fluctuating. Are they all over the place? In other words, are they bounded by some b that's very large or not? Is b fairly modest? Do they go to 0 as you approach the solution? So as x approaches the solution x star, does the variance of the gradient shrink? In that case, you can prove very nice things about stochastic gradient. But the sorts of rates that you see in the strongly convex case, you get an order 1 over k rate. And remember, for full gradient, we actually got a geometric rate. We sort of got a a row to the k rate. So you do pay a price for only using a stochastic gradient. Instead of having geometric or linear convergence, you only get arithmetic or sublinear convergence. If you've got convexity, you can say a little bit more, and so on. Yeah, in the case where the b is 0, you can actually recover the geometric rate. So if the variance in the individual gradients shrinks to 0 as x goes to x star, you actually get back the same behavior that you see in the full gradient method. Notice that all of these convergence expressions are an expectation, okay? Because these are random methods. They make random choices of j at every iteration. So we're not going to be able to prove a deterministic rate. We can only get an expected rate. Now, there's this modification to a stochastic gradient that's become sensationally popular, and it's called ATOM. And essentially, they just have a way of scaling the different components of GK in a clever way. They kind of keep track of the different components of the grad f of fjk at every iteration xk. They sort of keep track of them. And they use that to make a diagonal weighting of the GKs. And they can't really, people have proved things about this. There was a proof in the original paper, but I think it was wrong. But nevertheless, this is universally used in practice. And I checked last night, the paper has 115,000 citations. So it's become an absolute juggernaut. So that's what's used in practice. Okay, I mentioned that people had been proposing methods since about 2011 that are hybrids of the full gradient and the stochastic gradient method. And I won't go into detail about what they involve, but these are three of the most famous ones, SAG and SAGA and SVRG. Essentially, what SVRG does, to take one sort of typical example, is that every so often it evaluates a full gradient. And then in between full gradient evaluations, it kind of updates that full gradient by just evaluating individual grad f of xj's, just like stochastic gradients. So, you know, it really is a true hybrid of the two methods. And you can prove nice things about rates here. You can prove sort of linear rates that look more like the full gradient method. Okay, a little bit about coordinate descent. Again, not much because I don't have that much time left. But again, when you're trying to minimize a function h, unconstrained minimization, what you can do is instead of evaluating the full gradient, you can just pick one component of the gradient and use that to update one component of x. Okay, so you just take one partial gradient with respect to one component of x and just update that component of xk to get xk plus 1. This EI thing here is the vector with all zeros except for a 1 in the ith location. So it updates only a single component of xk. So it's like generally a cheaper version of stochastic gradient. It's been around, I don't know, since the 50s and 60s, but it's only recently that people got interested in proving convergence results for this method. The standard reference for the random version of this, where you just choose the coordinate to update completely randomly at every iteration, is due to Nesterov from 2010. I think it was published in 2012, but there's a very easy and elegant analysis for the fully random version. But in practice, people tend to use these so-called cyclic versions or random permutation versions. And these are versions where you just work through the components of x in order and then just wrap back to the start when you run out. So you can prove that they've got rates that are potentially, for some functions, they're potentially faster than full gradient descent. If the function satisfies certain properties, namely it's got these Lipschitz, the gradients satisfy these like component-wise Lipschitz properties. If that, okay, the convergence rates now depend on L max rather than L, which is the overall Lipschitz constant. And sometimes L is smaller than L max, so you can actually prove faster rates. Okay, I'm going to skip over those slides there. Okay, a little bit about conditional gradient. This is the Frank Wolf idea that I mentioned at the start. This is a very simple idea. You're trying to minimize f over some closed bounded, we actually need it to be bounded, convex set. So the idea is, let's suppose this is my set. I'll just pick some weird looking convex set here. The idea is that your point xk, you just look at which direction the gradient is pointing in. So let's suppose the gradient's going in this direction. And you just minimize a linear function using that gradient over the original set omega. So in other words, we're going to end up, I believe we're going to end up in this corner here if I do that minimization. So we call that point VK, and then we get XK plus 1 by just moving toward VK, but we don't go all the way there. We stop part of the way according to some formula. So we might stop here, and this might give us XK plus 1, okay? And we just repeat that process. So it's sort of like a gradient-based method, but it, at every iteration, it minimizes linear function over the original constraint set. So obviously, it's going to be useful if it's easy to do this, okay? It might be hard to minimize the original non-convex function over omega, but it might be very easy to minimize a linear function over omega. This is true, for example, when omega is like a box or a hypercube. It's trivial to solve this problem in closed form in that case, or when omega is a circle or something like that. There are many interesting instances where it's trivial to solve this problem, okay? You can show, by the way, I've omitted the theory, but the theory really does all fit on one slide. You can show that you get f of xk minus the optimal is order 1 over k. So you get a 1 over k type convergence rate. Again, it's sublinear. Okay, augmented Lagrangian. Let's see. Yeah, okay. Augmented Lagrangian. I'm just going to describe it for the equality constraint case. This has been around since, I guess, the early 70s. Estenese, Powell, Rockefeller, all invented it at about the same time. Rockefeller, by the way, is still very active, as many of you know. I'm going to be talking in a workshop in a couple of weeks in Seattle that Rockefeller is also talking in. I think he's like 85 now, but still extremely active. So the idea is you can write down a Lagrangian, which, as you know, is a very useful tool for defining optimality conditions for this problem. And you can add something onto it. You can add on sort of a quadratic penalty term that's 0 when the constraints are satisfied and positive otherwise, okay? And so, and then you get the so-called method of multipliers by picking some row, minimizing this augmented Lagrangian function over X for a fixed choice of lambda. You just fix your estimate of the Lagrange multipliers. And then you go the other way. You fix the XK and you update the lambdas according to this formula. And you just iterate like this. You might also adjust the value of rho from time to time. If you're not happy with how rapidly your iterates are becoming feasible, you might choose to multiply rho by a factor of 10 or something. That's what they're doing in the Lancelot code. Okay, there's a famous code by Lancelot by Congul and Twant from the early 90s, where they sort of turn this algorithm into something that's more workable and practical. Sometimes you've got additional constraints apart from the AX equals B. You can just handle them explicitly. If you also want X to belong to some constraints at omega, you can just add that into the first step here and just minimize that with respect to X in omega. So ADMM, very important method in recent times, again, invented by Eckstein and Bertsakis and popularized in this 2011 paper. So this is particularly useful when you can sort of partition the variables into two sets, X and Z. Got to remember to say Z here, so that you can break down the objective into two pieces, one depending on X, one depending on Z, and you've got a linear constraint that links these two things. And you might also have additional constraints on the X and Z separately, okay? So the idea here is you basically treat it like augmented Lagrangian. You write down the augmented Lagrangian for exactly this problem. So here's the augmentation penalty term, here's the original Lagrangian. But the idea is that you don't try to minimize. If you were doing the straight augmented Lagrangian method, you'd be trying to minimize this function jointly over X and Z, okay? But what ADMM does is it minimizes them separately. So it fixes the Z and the lambda and minimizes this thing over the X. Then it fixes the X and the lambda and minimizes this function over the Z. And then it updates the lambda according to this formula, okay? Now this might look like kind of just a bad, slow way of doing augmented Lagrangian, okay? Because why wouldn't you do better if you did this minimization jointly? But it turns out there are some recent papers, particularly by Eckstein, where they relate this, where they explain why that's not the right viewpoint. You shouldn't be thinking of this as kind of a, approximate version of augmented Lagrangian. You can relate it to other sort of iteration schemes that have been proposed in the past and show that actually it's superior in some senses to what you get by doing straight Lagrangian. Okay, and I'm pretty much out of time. The last thing I was going to say a little bit about primal dual algorithms, because I mentioned that at the end of last night's talk, that you could write a lot of interesting problems, regularized least squares, L1 regression, logistic regression, and so on, using this min-max of a function. And you could come up with these methods that take steps alternating between steps in X and steps in Y. The most basic one is gradient ascent descent. There's another one that's a very important one called PDHG, due to Chambol and Pock, which does something slightly non-intuitive, but again, it takes steps alternating between X and Y. And then we've worked on something recently, which I guess I did cite it here. I've done some work recently with various collaborators where we sort of enhanced these methods in various ways, using coordinate descent, using variance reduction, averaging the gradients, all that kind of stuff, and proving sort of optimal convergence properties. And so these are useful for solving very large scale problems in, for example, distributionally robust optimization. Okay, so I'll just finish by saying that there's a lot of things I didn't discuss. The rest is references, so I'm not missing too many slides here. So there's an awful lot of methods that I didn't discuss, some of which are quite relevant in data science. I didn't talk about Newton methods or quasi-Newton methods. People have been trying for, 15 years now to get second order methods and quasi-Newton methods working in data science problems. There's always just around the corner that there's a success close at hand, but as far as I know, it hasn't quite made it into production software yet. But that's no reason to stop trying. I didn't talk about, there are interesting methods for solving linear equations, by the way, that I didn't talk about. I've mentioned a couple of times in the last two nights that a lot of interesting data science problems take place over graphs and networks. And I haven't said too much about that, about algorithms for that. Also, a lot of problems in image and video processing. And they involve sort of specific choices of the regularization function. And you can use that to denoise and deblur images. And also, I didn't say much about integer formulations. A lot more integer programming people are getting interested in data science, so we'll probably see advances in that area. And I didn't say much at all about this very important area of parallel versions of all these methods. That's something I worked on a lot, between 7 and 12 years ago. Probably most famously, we have this paper called Hog Wild, which was in Europe's in 2011. It won the Test of Time Award at the 2020 Europe's, because it was kind of one of the first methods to sort of come up with a convergence analysis for a randomized parallel version of stochastic gradient. I haven't said anything about online learning. Okay, so thank you very much for your attention. Sorry, I've pretty much hit the top of the hour here, but if people want to stick around, I'm happy to answer questions.
Thanks a lot, Steve. Yes, any questions, please unmute your mic and go ahead.